finite fields and modular arithmetic, algebras, sets and accompanying properties, introduction to finite fields, multiplicative and additive identities, 0 and 1, and inverses, division and subtraction. Greatest common divisor, GCD, and lowest common multiple, LCM, Euclid's algorithm, Fermat's little theorem, Euler's theorem, and other key theorems and proofs and consequences, prime numbers, modular primes. Prime factorization, asymmetric nature of factorization and verification, applications in computer science, cryptography and hashing using prime numbers over finite fields. Number theory is a branch of pure mathematics that focuses on the properties and relationships of integers. Although historically considered abstract and theoretical, number theory has become highly practical in modern contexts, especially in the realm of computer science. Its foundational concepts, such as prime numbers, modular arithmetic, and divisibility, are crucial in fields like cryptography, where secure communication relies heavily on the difficulty of factoring large integers or computing discrete logarithms. Public key cryptographic systems like RSA and ECC are direct applications of number theory, providing the mathematical underpinnings for secure internet transactions, digital signatures, and encrypted messaging. In addition, number theory informs the design of efficient hashing algorithms, which are essential for data retrieval, database indexing, and blockchain technology. Algorithms rooted in number theory also play a critical role in optimizing computation and solving complex problems efficiently, such as finding greatest common divisors, primality testing, or calculating modular inverses. Number theory's influence extends to data structures as well, including techniques used in perfect hashing, random number generation, and error-correcting codes. Furthermore, computer security protocols frequently depend on number-theoretic algorithms to ensure data confidentiality, integrity, and authentication. Concepts include divisibility rules, modular operations, and congruences. Applications include hash functions, clock arithmetic in digital systems, and cryptographic protocols like RSA encryption. Prime numbers are only divisible by 1 in itself. With unique prime factorization, the sieve of Eratosthenes helps find primes. Applications include public key cryptography and random number generation. The GCD of two integers is the largest number that divides both. The extended Euclidean algorithm finds modular inverses essential for decryption. Applications include cryptography and optimizing algorithms by reducing fractions. Euler's totient function and Fermat's little theorem are key concepts. These are used in RSA encryption, digital signatures, and blockchain security. Systems of congruences involve solving modular equations. Applications include parallel computing and computer arithmetic optimization. Binary, hexadecimal, and other base systems are used for conversion between number bases. Applications include computer architecture, memory addressing, encoding, and compression. Carmichael numbers are examples of pseudoprimes. Probabilistic primality tests like Miller-Rabin are used. Applications include secure key generation in encryption systems and blockchain validation. Fermat's little theorem defines primality tests and cryptography. Bitwise operations involve binary-level number manipulation for efficient programming, encryption, and compression. Number theory plays a crucial role in cryptography, providing secure encryption through modular arithmetic and prime factorization. Algorithms utilize GCD and modular exponentiation for complexity and optimization. Databases use hashing for indexing and data retrieval. Digital systems rely on binary math, clocks, and cyclic counters. Security is enhanced through secure hashing, digital signatures, and key exchange. Modular arithmetic involves integers wrapping around a certain value, the modulus. The modulo operation gives the remainder of division. Congruence relation is when two numbers have the same remainder. Arithmetic rules apply to addition, subtraction, and multiplication. Applications are common in cryptography, hash functions, and computer algorithms. A finite field has a finite number of elements where addition, subtraction, multiplication, and division, except by 0, are defined. fields are equipped with operations satisfying associativity, commutativity, and distributivity. Finite fields are denoted as GFP, with P a prime number. Arithmetic is modulo P, and P must be prime for a field structure. Applications include cryptography and error-correcting codes. Modular arithmetic under a prime modulus forms a finite field. If the modulus is not prime, the structure lacks inverses. Applications include RSA, elliptic curve cryptography, and error-correcting codes. Digital signal processing and computer algebra systems also utilize finite fields. Euclid's theorem states there are infinitely many primes. The proof involves assuming a finite list of primes and deriving a contradiction. Every integer greater than 1 can be uniquely factored into primes. This uniqueness is foundational in cryptography. Fermat's little theorem relates to prime numbers and modular arithmetic. The fundamental theorem of arithmetic states every integer greater than 1 can be uniquely factored into primes. Fermat's little theorem is used for primality tests and cryptography. It states if P is prime and A is not divisible by P, then a to the power of P minus 1 is congruent to 1 modulo P. These theorems are essential for RSA encryption and digital signatures. Euler's theorem generalizes Fermat's little theorem. It states if A and n are coprime, then A to the power of Euler's totient function of n is congruent to 1 modulo n. The Chinese remainder theorem solves systems of congruences. Applications include computer algorithms and number puzzles. Wilson's theorem provides a primality test stating a natural number greater than 1 is prime if and only if the factorial of p minus 1 is congruent to minus 1 modulo p. Bézout's identity involves linear combinations of integers to find the GCD. These concepts are used in theoretical mathematics and solving Diophantine equations. Quadratic reciprocity involves the Legendre symbol, which determines if an integer is a quadratic residue modulo a prime. The law describes the relationship between two distinct odd primes. Proofs involve lattice points, modular arithmetic, or higher algebra. These concepts are essential in cryptosystems and understanding quadratic residues. Modular arithmetic involves standard operations on numbers without bounds. Modular arithmetic, known as clock arithmetic, wraps numbers around a modulus. It is used in cryptography, digital systems, and hash functions. Ordinary arithmetic is continuous and unbounded, while modular arithmetic is cyclic and finite. Both have distinct applications and properties. Modular arithmetic provides the backbone for cyclic structures in cryptography. RSA encryption uses two large primes to generate keys. Diffie-Hellman key exchange uses modular exponentiation for secure key exchange. Elliptic curve cryptography offers security with smaller key sizes. Modular arithmetic ensures one-way functions crucial for encryption. Prime numbers are essential for generating secure keys in cryptography. The larger the primes, the harder it is to factor the modulus used in RSA. Random large primes are tested using probabilistic primality tests. Safe primes enhance resistance to attacks. Prime numbers are foundational in ensuring cryptographic security. Hash functions use modular arithmetic to ensure deterministic outputs and uniform distribution. Cryptographic hash functions like SHA-256 use modular additions and bitwise operations. Hash tables calculate indices using hash values modulo table size. Security requires collision resistance and pre-image resistance. Hashing is essential for data integrity and security. Quantum computing poses a threat to traditional prime-based systems like RSA. Post-quantum cryptography is developing to counteract this. Key lengths must increase as computing power grows. Efficient algorithms are needed for large integers in real-time systems. Cryptographic systems must evolve with technological advancements to maintain security. In conclusion, modular arithmetic and prime numbers are cornerstones of cryptographic and hashing systems. Their mathematical complexity ensures data is encrypted securely. Digital signatures remain authentic. Hash functions perform reliably and consistently. As computing capabilities evolve, so must the implementation of these tools, but their foundational role in security protocols remains indispensable. Thank you for watching.